In our previous videos, we had taken a look at reviewing bond polarity and molecule polarity. And I told you all that this was going to be a foundational topic for this course. So what we're going to look at now is where that polarity becomes important. And one of the first places it's important is in dealing with intermolecular forces. So particles, whether they be ions, atoms, or molecules, have the ability to interact or stick to one another as a result of attractions between particles. These attractions, known as intermolecular forces, influence properties such as phase at a given temperature, melting and boiling points, viscosity, surface tension, solubility, and reactions. So we're going to take a look at the impact that intermolecular forces have on phase. So how can we explain phases at a particular temperature? We're going to look at judging who might have a higher melting point or boiling point based on intermolecular forces. And we're going to talk about solubility in detail. To understand these properties, it's important to understand the forces that influence them that's going to cause those particles to stick together. And there are four basic types of intermolecular forces. We have dispersion, dipole-dipole, hydrogen bonding, and ion dipole. These forces are going to differ by what types of substances they're found in, and they're going to differ by their strength. Starting from the top, going down to the bottom. The top we have our weakest forces. Ion dipole are going to be our strongest forces. Now that's relative because we can have substances that have only dispersion forces that are very, very strong, that might be stronger than some cases of hydrogen bonding. So it's really all going to depend on the molecules and the amount of attraction going on. But we're going to start off by taking a look at our dispersion forces. These may also be known as London forces, London dispersion forces, or you may hear them referred to as van der Waals forces. These particular forces are due to the movement of electrons. This movement is going to cause instantaneous dipoles. So dipoles, remember, occur when we've got that unequal sharing of electrons, where we've got one side more negative than another. In a polar bond, those dipoles are permanent. They're always there. The electrons are always towards one end of a bond or one end of a molecule. An instantaneous dipole is a temporary dipole, so it's not there all the time. It's going to be the result of the random movement of electrons. So we can look, for example, at helium. If we have a helium atom, we've got 2 protons and 2 neutrons in the nucleus, and we've got 2 electrons moving in that space outside that nucleus. Now, electrons are going to move around randomly about that nucleus, as we can see in these different frames. So these frames, imagine that we could take a snapshot at an instant in time. Those particles don't stay there. The electrons are constantly moving. It's just in one instant they're there, and another instant they're somewhere else. So looking at frame 1 and 2, the electrons happen to be on opposite sides of the nucleus. So that's going to give an even distribution of our electrons. We've got negative charge on both sides. But in frame 3, just based on the random movement of our electrons, the electrons happen to end up on the same side of the atom. This is resulting, so here they're on the same side, that's resulting in that sudden buildup of negative charge on that one side of the atom. So in that particular moment, we have one side partially negative, the other side partially positive. So that gives us that temporary uneven distribution of electrons, leading to a temporary dipole and partial charges. Now, if that helium atom is sitting all by itself, we're going to have this random fluctuation between no dipole and a dipole. Now, this becomes significant if that atom is near another atom. If it is near a neighboring atom, it has the potential to induce a dipole in its neighbor. So when we say induce, that means it's going to force a dipole. That sudden buildup of negative charge on one side of one helium atom is going to repel the electrons in another helium atom, pushing them to the other side, then forcing that atom to form a dipole. So say in our image here, we have our central helium atom here. When this charge suddenly builds up here, it's going to push those electrons to the other side. So my center atom here had a temporary dipole. When that dipole formed, it was close enough to another helium atom that it pushed that helium atom's electrons away, because remember, negative charge repels negative. So we get the negative built up on one side, leaving this side positive. Same thing in our other atom. We can induce that dipole. Now, that causes these neighboring atoms to have opposite charges, and opposite charges from the temporary dipoles and induced dipoles can then attract one another. It's that attraction that is our dispersion force. So our dispersion forces are found in all substances. They are the weakest of our four forces. Their strength depends on polarizability. So that's a fancy word for saying the ability to form a dipole. How well we can form that dipole depends on size and surface area. Larger substances with more surface area experience stronger forces. So here we have the example of comparing pentane to 2,2-dimethylpropane. So here comes our organic chemistry back. We've got that straight chain structure versus its isomer with the branch structure. Notice with the straight chain structure, it's longer. It has more surface area compared to that very compact, almost spherical in shape structure for that 2,2-dimethylpropane. It's got less surface area. As a result, that pentane is going to experience stronger dispersion forces compared to the dimethylpropane. And we can actually see this reflected in the boiling points. We see the boiling point for pentane is 309.2. The boiling point for that dimethylpropane is 282.6. The pentane has the higher boiling point because it has stronger forces. Stronger forces hold on to each other better, and therefore it's harder to break. It requires more energy to separate them and therefore boil. So, first thing we're asked about is, why would a longer molecule have stronger dispersion than a more compact molecule? We've kind of addressed that already. Part of that, having that longer molecule, means it has more surface area. More surface area means more points of contact. So I like to use the analogy of a piece of tape. So say you've got a poster that you want to put on the wall, and the only thing you've got to put it up with is tape. If you take just a small square of tape and you attach it to that poster, you've got a very small surface area. That small surface area, when you attach it to the wall, isn't going to stick very well. You're not having a very strong attraction. If you use larger pieces of tape, it gives you more surface area, more points of contact between the tape, the poster, and the wall. And therefore, you get that stronger attraction, that a better ability to hold. Same is true for molecules. The larger the molecule, the more surface area we have, the better ability those particles have to stick. Now, next we're asked about why an atom of potassium would have a stronger dispersion force than helium. So we said our strength depends on size. So longer and larger substances. So here, if we're talking about atoms, if we compare potassium to helium, potassium is a larger atom. So we've got to remember our trends for atomic radii. Remember, our trends are that as we go down a group, size increases. As we go across a row, size decreases. So we actually increase going from right to left. So the atoms towards the lower left-hand corner or lower in the periodic table are larger than atoms in the upper right-hand corner. So a potassium atom is larger than a helium atom. So if we think about why remember, larger atoms, their valence electrons are further from the nucleus. If my electrons are further from the nucleus, they're going to be held less tightly. If they're held less tightly, we're going to be able to push them around a whole lot easier. And remember that strength is based on polarizability. How easily can we push those electrons around to induce those dipoles? If potassium is not holding its electrons very well, it's going to push them easily. We're going to get that induced dipole more easily, and therefore we're going to have that better likelihood of forming forces, and they're going to be stronger because the electrons can stay in that configuration. So we want to be able to compare strengths of forces. So we're given a series of atoms, and we are asked to rank them based on increasing dispersion forces. So they're all atoms. If they're all atoms, we're going to be looking at atomic radii. So when we go to rank these atoms are all located in the same row in the periodic table. So we said the trend is, as we go across the row, the size gets smaller. So the atoms further to the right are the smallest. So that's going to make my argon the smallest, then my chlorine, phosphorus, silicon, aluminum, magnesium, and sodium. So my sodium is the largest. As the largest, it's going to have the strongest dispersion. My argon is the smallest. It's going to have the weakest dispersion. So if we're looking at comparing individual atoms, we are looking at atomic radii. The larger the atom, the stronger the dispersion force. Question 4, we're taking a look at molecules. We're asked which of the following molecules has the weakest dispersion force. So with molecules, we are looking at size. So I've got CH4 versus a CH2, CH2. The weakest force is going to be my smaller molecule, the CH4. It's very compact. It's not going to stack very well. It has few atoms that can experience dispersion, so it's going to be the weakest. The CH2 is larger. It's slightly longer. It can stack better. It's going to have more points of contact, greater surface area, so it will have the stronger dispersion forces. So that is just our first intermolecular force, the dispersion. Again, they are found in all substances. They are the weakest, but their strength varies with size. So as the molecules become significantly longer, the strengths become significantly stronger. In our next video, we're going to take a look at some additional intermolecular forces.